Hello students, we will be doing now the video 5 on capacitors, okay, and this video 5 is on the dielectrics, okay. This might be a new term for you, okay. Actually dielectrics, these are a special type of materials, okay, like you know that any matter based on the conductivity, all right, based upon their conductivity, okay, we are classifying them into three categories, right? You know about it. One is conductor, we even call it good conductors, right? Another is semiconductor, as the name, the conductivity is in the semi range, and another is insulator, okay, insulator. Now this, all these materials, okay, behave in a different way when kept in a electric field, okay, like applying the voltage, that is what electric field only, isn't it? So let's see how they are behaving in a electric field, okay. Let's say let's say there are two plates of a capacitors, okay, capacitor, okay, negative, all right, plates of a capacitor, okay. Now in between, now the capacitor we used to write by this way, right, isn't it? But for simplicity I'm not going to write it anymore this way, I'm simply writing this way, okay. It means the capacitor, and such that the electric field outside is 0, electric field outside is 0, right. While the electric field in between is what is sigma by epsilon naught. This we had learned in the previous video. Now let's do one thing, okay. Let us keep the conductor and let's see how the conductor will be going to behave, okay. Conductor means what? Number of free electrons will be there, right. The electrons are free to move within the conductor, right, but the electrons cannot leave the conductor, isn't it, right? And we know that as the electrons are so free, that's why they can conduct the electricity also. Now this positive plate will attract the electrons, and the electrons will going to settle near the surface facing the positive plate, right. If the electrons are settling this way, then this side will have the scarcity of the electron, that means it will become automatically positive, right or not? Now outside the electric field was setting up this way, right, this is the direction, but inside the conductor, how the electric field is setting up, the electric field is setting in an opposite way, all right. The electrons are so free and so many that in a conductor, these the opposite electric field will also be exactly equal to that of the inside, all right. It happens in a conductor. That means within, what is the within the conductor, okay, within the conductor, how much is the electric field? Electric field is 0. Why? Because the total field, when we see in terms of vectors, the total field is how much? Electric field due to the external agency and electric field due to inbuilt, right? External agency is E naught, inbuilt is opposite, so it's also E naught minus. So what is the total? 0. So electric field within, okay, within the conductor is 0, okay. This is known as, even this is known as electrostatic shielding, okay, shielding, okay. One example I'll let me take is that if there is lightning, okay, if there is lightning and you are within a car, then the chances of your safety increases, right? Because mostly the car body is made up of what? Is made up of metal, right? So inside the metal, electric field is how much? 0, right? So if no charge flows through it, you're not going to get the shock, all right. So this process is known as electrostatic shielding. But in a car, there is no guarantee that you are within the what to say, completely within the conductor, because there are tires and the other part also, right? Okay. And that's why sometimes it is that is you have given the question also. Suppose this is a conductor, all right. Here is a, let's say, okay, let's say here is a stool. Okay, stool means made up of wood. Let's say this is a metal. Okay, this is a metal. Okay, and within the metal here is a wooden stool. Okay, let's say this is wood, made up of the wood. Okay, wooden stool. Okay, and here is a man standing. All right, and on the surface, okay, high voltage is given. High voltage have been given, very high voltage. Now the question is, will this man get shock? Okay, will this man get shock? Okay, let me make it further complicated. See, the body of the metal is very thick. Okay, all right. Okay, now will the man will get the shock? The question is no. Because what? Inside what? Electric field, however strong field you give here, inside the electric field will be zero. So the man will not going to get any shock. And this is known as a electrostatic shielding. So you need to remember one very important point. You need to remember, inside the conductor, in an external field, okay, the electric field inside the conductor always is zero. The net field is always zero. All right, fine. So that is one thing you can remember. All right, now I'm not going to talk about the semiconductor. Now coming about the insulator. Insulator, the electrons are not free. The electrons are so tightly bounded that they cannot move. So what will happen? As if the electrons cannot move, all right, if the electrons cannot move means what? The charge cannot flow within the insulator. So will the electric field will have any effect? The question is no, it will not have any effect. Okay, but apart from this insulator, conductor and semiconductor, okay, there is a special class of material which is known as a dielectric. Okay, dielectric, sometimes it behaves like an insulator, but it allows polarization. Okay, it allows polarization. This is the only difference. Okay, they are in this material, this dielectric, what? The electrons are tightly bounded. They resembles the insulator. Okay, dielectric, they, what to say, they resemble, what to say, insulator. Okay, some book even written as insulator, because many of their behavior is somehow same as that of the insulator, but what it say, it allows polarization. This is the only difference between what to say, dielectric and insulator. Okay, now what happens in a dielectric when electric field is kept in is placed? Okay, now again let me suppose that these are the parallel plates of a capacitor. Okay, I'm making it further away simply just to make things clear. Okay, now suppose I have kept a dielectric slab. Okay, now the dielectric examples, we can have paper, this is a dielectric, mica, okay, glass, these are some of the dielectrics. Okay, now what to say, another one more thing, that in order to tell the dielectric characteristic of the material, we have one quantity which is known as a dielectric constant. Okay, dielectric constant means what? See, if there is a person, then we give them a name. If there is a person, we give him or her a name, isn't it? Similarly, in order to tell about the dielectric material, about its property, we have a quantity which is known as a dielectric constant. Like the dielectric constant of paper will have one value, mica will have one value, glass will have one other value. Okay, so different materials, if it is a dielectric, it will have certain finite value. Okay, and these are the some of the examples. Okay, now suppose this is a dielectric, say. Okay, we need to understand. Okay, now what I say, that dielectric allows the polarization, right? The electrons, even in this case, also tightly bounded, however it allows polarization. Now what happened, there is an external applied field, right? And the external applied field, let me call it E0, is equal to the charge density by the plate area, right? Okay, this is the one. All right, now within the dielectric, what happens, the atoms or molecules, whatever we call, they undergo what happened, they undergo the polarization. Okay, means what, that the electrons of it will get little bit, the electrons of it will get little bit polarized. See why I said little bit, because dielectric resemble the insulator. Okay, so it will not get polar. If it gets strongly polarized, then what will happen, the bonds will get break free, the electrons will be free, then it will behave as a conductor, isn't it? So this is not the case, they get slightly polarized only. Okay, so this side negative and this side positive, right? I'm just giving two atoms, molecule, or whatever the entity we are talking here. Okay, so this also gets slightly polarized. Polarized means it have to be negative, this side have to be positive, this negative, this side have to be positive, right? Isn't it? Similarly, this is negative, this is positive, this is negative, this is positive, right? Gets negative, positive. So I'm just showing here the two entities only. Okay, two entities, plus, similarly minus and plus, similarly minus and plus. All right, now you can see here that this plus and minus, they will cancel out each other, in this case also, in this case also, in this case also, in this case also, right? But at the edges, all right, what is remain? Negative is remain, positive is remain. So finally this figure, in a better way, can I make it this in this form? All right, this figure, these are the parallel plates capacitor. Okay, these are the parallel plates capacitor. Okay, this is a dielectric, right? Okay, this is a dielectric. Now at the edges, the charges will get settled, little bit of charge will get settled in such a way that on its edge it will have negative, on the other edge it will have the positive, right? Outside, the electric field goes from plus to minus from the plate. However, the inside, the electric field goes where? EP. I'll call due to the polarization. So what happened within the dielectric? Okay, I'm talking about within the dielectric. Okay, within the dielectric, how much is the electric field? Within the dielectric, the electric field will get within. Okay, within the dielectric, the electric field is outside electric field minus the electric field due to polarization. Okay, so what, the electric field, the net field when the dielectric is placed is get what? Reduce. All right, the electric field will get reduced. Okay, all right. Okay, the electric field reduce when you keep the dielectric between the plates of a capacitor, the electric field is reduced. Okay, to tell that, the same thing, to tell about the dielectric property, we have one quantity which is known as a dielectric constant. Okay, dielectric constant. To talk about the dielectric property of the material, it is denoted by K. All right, now what happened is, if dielectric is kept, then within the dielectric, the electric field get reduced by K times. Alright, like for water, okay, the dielectric constant is 80. Okay, I'm just taking this. For water, it's 80. Some book writes 78 also. That is distilled water and mineral water difference. Okay, so let me write for 80. Okay, means what? If the water is kept in between, within the water, the electric field get reduced by how much? 80 times. Okay, this is the information. So what you need to remember is when the dielectric is kept, the electric field get reduced by K times depending upon its dielectric constant. Okay, now why we are learning this thing? See, I have simply chosen a topic dielectric. We are learning capacitor, but still we are learning dielectric. The reason is because, okay, the reason is because capacitance is equal to what? Charge by potential, right? And the potential electric field is equal to minus dV by dr, right? Isn't it? Now, if the electric field is reducing, all right, then dV will also reduce, right or not? Okay. If the potential is reduced, now you see, I will tell the story. See, minus has nothing. It just tells the direction only. So I'm not going to write any. So this is equal to what? EDR, right? Isn't it? Electric field reduce because of the presence of dielectric. If the electric field is reduced, what it will reduce? dV will reduce. dV means what? Potential. If dV is reduced means what? V is reduced. V is reduced means what? C increases. Means what? It means when the dielectric is kept in between the plates of a capacitor, the capacitance increase. Okay, the capacitance increase. That's why dielectric is very, very important. Okay, understood. So the sum up line is dielectric. They are special class of materials which resembles the insulator, not exactly the insulator, which undergo polarization. Okay, to tell about this characteristic, we have a constant which is known as a dielectric constant. It is denoted by a symbol of K. Okay, and the electric field get reduced by K times when the dielectric is kept within the medium. All right, how it reduces, I have given this. You need to understand this. As the electric field get reduced, what will happen? Electric field reduce means potential reduce. Potential reduce means capacitance increase. I hope you will understand it. Thank you.